Hello guys, welcome back to my channel Gamma. So in this video I actually said to myself, let's make let's start making some linear algebra videos, but from a sequential manner. So this video that I'm making is about row reduction and like the introductory video to general linear algebra. So let's get started. Okay, so like most of my introductory videos, let's start with breaking up these words. Linear, as you can see, it's related to lines. So let's take equation of a straight line, say 2x minus 4y is equal to 3, for example, and take another equation, x plus y is equal to 5. They're perfectly linear equations, and I'm sure most of you will agree. Now I'm sure you've done this before in the exam, if they or anywhere else, if they tell you to solve this system of equations, linear equations, simultaneously, what you do is you notice the 2 down here, and which is the coefficient of x for the first equation, and 1, which is the coefficient of x in the second equation. You try to basically match the coefficients by multiplying this equation, the bottom equation, by 2. So we get 2x plus 2y is equal to 10 in the bottom equation, and then you want to get rid of the x. So what you do is you subtract the bottom equation from the top equation. So when I do that, the positive 2x, negative 2x will cancel off. We have negative 4y, negative 2y is equal to negative 10 plus 3 is negative 7. So negative 6y is equal to negative 7, which implies that y is nothing but 7 over 6. Okay, and then if you plug this value in any of the equations, you get that x is 3 by 2 plus 7 by 3, which is like 9 plus 14, which is like 23 over 6. Okay, I mean, solving this was not like the main goal, but it's about generalizing this process. So notice how we multiplied this equation to match coefficients and then subtracted that from the top equation. So the idea I want to talk about before moving on to the more practical aspects of linear algebra is this notion of generalizing whatever black magic we did over here. This, you have to admit, this was a clever technique of elimination. We call this elimination. So the idea is about generalizing this. I mean, this was for, say, 2 equations with 2 variables or 2 unknowns. This is about generalizing this idea to a system of equation that looks somewhat like this: a11 x1 plus a12 x2 plus dot 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 a1n xn a21 x1 plus a22 x2 plus dot 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 a2n xn, and this is equal to, say, b1, this is equal to, say, b2, and we can do this, say, for m am1 x1 plus am2 x2 plus dot 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 amn xn is equal to bm. Okay, we want to generalize this process of elimination for a system that looks like this, which has basically m equations and n unknowns. So these x with the different subscripts are the unknowns or the variables. And m and n may not always be equal, and we'll look at those examples too going forward. I mean, the general idea of linear algebra is using matrices to represent like big bulky stuff like this, because we want a more compact way. We want to write this system of equations as one unit. I mean, that's probably the reason that why we call them a system of equations, because we want to treat them as one unit in whatever we do. So we use matrices, which are basically array-like representations, where we take all of these coefficients, say a11, and then in the row we write the coefficient that's to the right of it, a12, a1n, a21, a22, a2n, am1, am2, amn. This matrix multiplied with the unknowns is equal to, well, these b1, b2, bm. And this is a way more practical way of writing, because we can just call this matrix, say A, capital A. We can call this, I don't know, capital X. We can call this guy B. So this starts looking a lot more like like the case if we had, like, say, one linear equation, except the A is a matrix, the X is a vector, and B is also a vector. I mean, but the general idea is the same. Okay, so when we talk about like elimination, you notice we multiplied some equation by some constant scalar value and then subtracted that from an earlier unchanged equation. So this process that we did once is called one row operation, and it turns out you can keep doing them. I mean, in our case we didn't need them, but if we had, say, 3 equations and 3 unknowns, we would probably have required a few more steps of elimination, which involve more row operations. So a row operation, I'm going to define it. Is basically multiplying a row by a non-zero number and adding or adding to or subtracting from a fresh row which is basically unchanged, which is because we didn't multiply the first equation, we just multiplied the second equation and then subtracted that from the first equation. So adding to or subtracting from a fresh row by this multiplied row that we got in this step, the first step. So there's 2 steps in all. First is multiplying the row and then adding or subtracting that from another row, fresh row. Okay, now so this is the idea of generalizing it. I mean, here we did it once, one row operation. For a system like this, we may require them a multiple number of times. But now the most logical question to ask it, okay, fine, if we are going to use this method of row operations, how do we know when to stop? because I mean there might be some stop point beyond which there's no point in doing any row operations. I mean here it was pretty evident that like one variable disappeared. So like a variable disappears on because of this subtraction, multiplication and subtraction, because we matched the coefficient and then an entire variable disappeared. But we need a more solid way of knowing when to stop, and that's when reduced forms, or if you want to be more old school with it, you can call it row reduced echelon forms. These are the most reduced forms. Row reduced echelon forms are the most reduced forms, because for other normal reduced forms you just like don't simplify it that much. So we're gonna talk about this. We call them RREF. We're gonna talk about them on a fresh page and how they are a nice way of letting us know when to stop the row reduction algorithm. Okay, so RREF, row reduced echelon form, is basically a state, is a state of a matrix, a state that a matrix can be in. And how do we know whether a matrix is in row echelon form? Well, rows of zeros are at the bottom, like entire rows of zeros. Any row that is not 0 starts with a 1 and is called a pivot. So other entries in a pivotal column, basically the column that contains this pivot that we talked about, are 0. And a pivot of a lower row is to the right of the pivot of a higher row. No, now I'm sure at this point, by this time, this feels like a lot of mumbo jumbo. I mean, I felt the same too. But nothing explains stuff better than an example. So let's have a matrix here. We have 0, 1, 2, 1, 2, 1, negative 1, 0, 1, 2, 0, 0, 1, 1, and negative 1, 2, 1, 1. I made it a little longer for more practice. Okay, so before doing this, I would like to give you like a general idea of what a row echelon form can look like. So a row echelon form can look something like this. 1 here, which is basically the first pivot, and since this is in the pivotal column, this is the pivotal column, all the other entries are 0. Then in another column there might be some entry here and like rows of zeros below it. Fine. And since you can't do anything with this column because you can't have a 1 over here in this place, you move to the next column and then you get a next pivot over this. So this pivot is 1 row lower than the previous pivot, like the 4th point over here, and then the pivotal column has zeros everywhere else, and probably like some arbitrary element here, so you leave that column, probably leave this column 2 again, and then the next pivot is over here. I mean, just because you left a column doesn't mean you can skip pivot positions. You need to go one row down exactly whenever it is convenient, whenever there's like not a 0 there, unlike these columns. And then basically finally you get the last pivot down. So this is somewhat what a RREF, a matrix in RREF can look like. Now let's do this example. Okay, so we need a pivot at the topmost corner of the left, just like this. We need like a pivot like this. So what we do is use this row operation, and this row operation is valid. It's exchanging rows 1 and 2, which is basically like saying you have one equation, you have another equation, just take the bottom equation on top, the top equation on the bottom. I mean, honestly, it doesn't change what the system is trying to describe, so we can totally do that. And we'll have 1 0 2. This entire row will go on top. 2 1 1, 0 negative 1 1, 0 2 0, 1 1 negative 1, 1 2 1. Now what you do is, since we have a pivot here, the other entries in this column should be 0, so we want to get rid of this 2. So what we do is we change the third column into third column minus 2 times first column. So when we do that, I had 1 0, 2 minus 2 is 0. We need to do that for other entries too. We'll have 2 1 negative 3 here, 0 negative 1 1, 0 2 0, 1 1 negative 3, 1 2 negative 1. Fine, we established a pivot here. Now let's move on to the next column. Well, we already have a pivot present in its proper position. We need to get rid of the 2 and the negative 3. So what I'm going to do is I'm going to take row 1, change it to row 1 minus 2 times row 2. I'm going to take row 3, change it to row 3 plus 3 times row 2. Always use this pivotal entry. Always scale the pivotal row, because now in the previous pivotal column that won't make a change because we have a 0 there. It's a sequential algorithmic process. Then here we have 0 1 0, 0 2, negative 1 2, negative 4 2 and a 6, negative 1 1 0, negative 3 2 5. Now moving on to the next column, notice we have a 2 here, actually a negative 2. So what I'm going to do is I'm going to divide this entire row 3 by negative 2 so that I get a 1 there. 1 0 0 0 1 0. Fine, and even after I get a 1 here, I would like to do something extra. I would like to get rid of the negative 1 and the 2. So what I would do is basically change row 1 to row 1 minus 2 times row 3, and this is after we divide everything by negative 2. And then row 2 changes to row 2 plus row 3. So we get 0 0 1, and we have 2 negative 1 negative 3 minus 1 1 0. We'll have 2 negative half and negative 5 over 2. Now notice we have 3 pivots and we can't go any further because we're basically running out of rows. And that's why I wanted to point out in such matrices where there are more columns than rows, there's always going to be some columns that don't have pivots. We're going to always have these non-pivotal columns, and you call them free columns. I mean, I just wanted you to realize this first. We're always going to have non-pivotal columns when there are, like, the column number is greater than the row number, because you're basically going to run out of any more rows to put pivots in. I mean, if we had like another row, we could have achieved a pivot here and gotten like another pivot, because we're going in like a sort of diagonal fashion over here. I mean, the way I think about it in essence is RREF, like converting anything into RREF by row operations, row reductions, is basically trying to get as close as possible to the identity matrix. Now the identity matrix is a square matrix where the rows are equal to columns, but you know, in these special cases when columns are greater than rows or rows are greater than columns, this is the best, this is the closest you can get to an identity. You just can't help that these other columns won't have pivots in them. And we talked about columns greater than rows here. In the next example, I'm gonna do a row greater than columns case. Okay, so now we have this matrix: -1 3 -3 2 -3 -3 -3 0. Okay, now we are going to convert this into RREF. So what I'm going to do is take row 1, change it to -1 times itself. We get rid of the negative sign here. 1 3 -3 2 3 -3 -3 0. Now we got a 1 here in the pivotal position. Now let's eliminate all these other numbers, change them to zeros. So we can change row 2 to row 2 minus 3 times row 1, row 3 to row 3 plus 3 times row 1, row 4 to row 4 minus 2 times row 1, and that's when we get 1 0 0 and 0. But here we have 3, -12, 6 and a -6. Okay, fair enough. We got a pivot in the first position, and we need a pivot over here in place of -12. So in order to make that into a 1, we divide row 2 by -12 throughout. Since this is a 0, that's the advantage we have here. We have 3, 1, 6 and -6. Now we got a pivot. Let's eliminate all the other numbers, make them zeros in that pivotal column. So 1 changes to 1 minus 3 times row 2 actually. Row 3 changes to 3 minus 6 times row 2. row 4 changes to row 4 plus 6 times row 2, and we have 1 0 0 0 0 1 0 0. Okay, fine, we got pivots in all the columns, we got pivots in all the columns, but again, this is the best we can get to an identity matrix, because an identity has ones along the diagonal throughout, like, you know, touching from the top left corner to the bottom right corner. And we can't have, you know, ones, you know, touching the bottom, because there are not enough not enough columns now. There are more than enough rows, but there are not enough columns now, in the case where the rows are way more than the columns. I mean, and like the previous case of columns greater than rows, it's not necessary that there won't, it's not like a inevitable fact that there won't be any there will be any free columns. You can have pivotal columns, as you can see in this example. These are clearly pivotal columns, but again, you may or may not have pivotal columns, just like a regular square matrix case. It's only in the columns greater than rows that you will never have all columns to be pivotal columns. And very briefly, I would like to tell you that if we have like a square matrix where the rows are equal to columns, the best case you can have is pivots in all columns, and the final matrix is exactly the identity. I mean, it perfectly resembles the identity after that. That's the best case. A less favorable case, I'm still saying less favorable, because this is still, a square matrix is still better than rectangular matrices. Less favorable cases that pivots in some columns, the others are non-pivotal or free columns. Now in this case, R greater than C, it's like this, except it won't be identity, it'll never be identity. But in the C greater than R, the columns greater than row, it's always going to be the less favorable condition. That's basically the idea. And in the next video, which is probably going to be part 2, I'm going to extend this notion of row reduction to solve systems of linear equations, because that's the entire purpose of linear equations, right? I mean, at least linear algebra. We want to do some algebra on them. We know we know now what linear means, and what it holds for us. Now we want to do some algebra. We want to solve systems of equations like n, you know, like I said on the first page, there's n unknowns, m equations, and the two ideas we'll be focusing on throughout this linear algebra sequence, and even when you go ahead and do some differential equations, partial differential equations, is uniqueness and existence of solutions. I mean, does a solution first exist or doesn't exist? And if it does exist, then is it unique? Or no? And if it doesn't exist, then there might be some geometric interpretation to why it doesn't exist. At least that's how I put it. So stay tuned for the next video. Guys, please like, share and subscribe to my channel. Recommend me to your friends, spread the word of gamma digamma in the math community, yada yada yada. And in the meantime, peace out.